Alright, so today we're going to be starting some work in Chapter 13. And so we're going to be looking at antiderivatives, what they are, what they can be used for. And so I think you can probably tell the prefix anti means not or opposite, right? So it's important that you have a pretty good understanding of derivatives before we can really talk about antiderivatives. But a function f is said to be an antiderivative of f of x on an interval if, when you take the derivative of that, you get the original f of x back again. So rather than taking the derivative, you're looking for a function that would give you that equation as its derivative. So that's hence the anti term. All right, so let's talk about it, and then we're going to talk about notation. So first of all, an antiderivative of f of x equals 2x. So you're thinking of something that what would a function look like that when you took the derivative of it, your answer would be 2x. Okay, so notice f of x could be x squared. Okay, and I say could be because there's actually multiple things it can be. But the reason this one is an antiderivative, okay, keyword being an, meaning there's more than one, is when you take the derivative of x squared, you get for a result 2x. But this is just one answer. And in fact, we're going to have a set of answers because it's just one antiderivative, because let me bring up another one that would have worked. X squared plus 3 is also an antiderivative for f of x. Because notice if I take the derivative of x squared plus 3, I also get 2x. Okay, so again, it's kind of like you have the result already, you have the derivative already, and you're trying to backtrack and decide what the function would have been. So notice really any constant could have been put here, right? And that's because if you take the derivative of a constant, you just get 0. So if you want to talk about the set of all antiderivatives, it's basically going to look like whatever the function that would give you that as its derivative looks like, plus or minus a constant. In other words, in our example up there, it needed to have the x squared part so that it would have a derivative of 2x, but it could have been any constant being added or subtracted at the end, and it still would have worked. So it's going to be g of x plus c, where c is a constant. So just like we had with derivatives, we're going to have rules and processes with antiderivatives as well. So the process of finding all antiderivatives, the action, it's a verb. Well, integrating is a verb, but the process is called integration. So if you're asked to integrate something, then that just means find the antiderivatives. So before we can really get to some examples, we do have some notation and some processes that we need to be aware of. So the symbol for integration, the symbol that tells you, hey, I need to integrate something, looks like this. It sort of looks like an S, but it's really an operation sign. This is called the integral sign. So here's the notation as you will see it. You'll see this little integral, and then you'll be given a function to take the integral of. Okay, and you will always see that ended with d something dx or dt or dy. Whatever letter follows d just tells you this is a part of the notation of every integral. Okay, so this is just a notation. In other words, you need to get used to writing it. It just means with respect to x. So if you remember our notation for derivatives that was like d over dx, and we read that as d dx, that's all it means. It's just letting you know, hey, that we're going to find the antiderivative using the variable x. Okay. Okay, so this means find the set of antiderivatives of the function f of x with respect to x. That's what it means. Okay, so using our example above, if I asked you to integrate 2x dx, okay, now this is not a multiplication, this is a notation. So you just need to get used to seeing that on the end of integrals. It's always going to be there. So what I'm asking you to do, we already did the answer to this one, right? So I'm asking you to tell me what the equation would look like that would give this as its derivative. Okay, so notice it's x squared plus any constant. Okay, so this would be the answer, but the reason it's the answer is because if you take the derivative of x squared plus c, notice you get 2x if you do the power rule right. The derivative of a constant is 0, or you just get 2x. So it's like working backwards. It's like I already know what the derivative is, and I'm trying to backtrack and get the original function. So remember what I said, the more you understood derivatives, the easier the concept of antiderivatives will be. So some of us might find that antiderivatives are a challenge because we never really learned derivatives all that well, and that's going to be a problem. So it's definitely something you need to review. That's not a quick review. We've talked about derivatives for most of the semester, so it's definitely something that's not going away. That's really the essence of calculus. Okay, so first of all, we call all of the integrals we're talking about today what we call indefinite integrals. Okay, and in other words, it's just an integral sign without a start or a stopping point. Okay, we're going to learn some later on where we will have a starting or a stopping point, and those will be called definite integrals. So, but for now, all of the ones we'll do will be indefinite. All right, so we're looking for the antiderivative of k dx. Now k is just a constant. So like it might be 3 or 4 or 10 or negative 20. Okay. So remember what you're looking for. You want to know which type of function would give you just the number k as its derivative. And that would look like kx plus c. So I don't want to show you the check step on all of these, but an example might be, we'll look at one in a minute maybe, but what would the derivative of, for instance, 3x be? The derivative of 3x would be 3, right? So again, we're just going backwards. We already know the result. We're trying to figure out what the original must have been. All right. Just like the power rule for derivatives was important, the power rule for antiderivatives is going to be equally heavily used. So just so you know, this is as long as n does not equal -1, okay, n being the power. So if you want to find the antiderivative of x to the n power dx, again, remember, every integral will end with dx. It doesn't mean multiply, it just means, hey, we're going to use the letter x. That's all it means, okay? So remember our rule for derivatives, right? We move the power to the front and we reduce the power by 1. Okay, well the rule for antiderivatives is leave a little space here. We're going to bump the power up by 1 because we're going backwards, okay? And then we're going to multiply by 1 over that new power. And then we always end it in a plus c so that we have all the forms. All right, so let's do a couple of examples. This will take a little getting used to because, again, we're just so used to doing derivatives, hopefully, that antiderivatives are a little strange, right? So the power rule just says if I want to do the antiderivative, I will bump, so I'm going to leave a space, bump the power up by 1 or add 1 to the power, and then multiply by 1 over that new power, and then don't forget your plus c. Okay, so this is my answer. Okay, but let's check it. And you can do these with all problems, and particularly while you're starting, it might be a good idea for you to check it. In other words, when I take the derivative of this, I should get back the original again since I'm doing antiderivative, right? So notice, if I bring this power out to the front, 4 times 1/4 is just 1, right? So I end up getting 1 x to the 4th plus, sorry, not x to the 4th, but x to the 3rd, right? So notice what I forgot, right? I moved the power around to the front and I forgot to take 1 away from the power. And then plus 0, right, which is just x cubed. Okay, so I'm just going to put a check mark, right? We got back what we started with. Okay, so that lets you know that you did antiderivative correctly. So remember this rule. It doesn't matter what the power is. You're going to add 1 to the power when you do antiderivatives, and you're going to multiply by 1 over that new power. Okay, so be careful, use a calculator if you must, but what is negative 5/4 plus 1? That would be negative 1/4. So negative 1/4 is the new power, and so you will do 1 over that new power, and then don't forget your plus c. Okay, so I don't care if it's a fraction, I don't care if it's a negative number. You add 1 to the power, you multiply by 1 over the new power. Okay, so when we have a number divided by a fraction, we can just flip the fraction. In other words, 1 divided by negative 1/4 is the same as 1 times negative 4 over 1. So again, you can check that in your calculator if you don't believe me. But this is negative 4x to the negative 1/4 plus c. Remember, this is what I want to see, right? I don't really want to see negative exponents in your final answer. Okay, but let's check it real quick. Let's see if it works out. So, in other words, when I do the derivative of negative 4x to the negative 1/4 plus c, notice I use this version, right, because it's easier for me to take the derivative of that. So let's think about that. If I move this power to the front, right, I'll get negative 4 times negative 1/4, which is just 1. And then if I subtract 1 from the power to find the derivative, right, then I'll get negative 5/4 plus 0. Notice that's just x to the negative 5/4. So again, I get the original back again. All right, so our third rule for finding integrals is some of these rules are really long. You're not going to need to remember like what the rule is called. You're just going to need to know how to do it, how to perform the operation, not necessarily. I'm not going to say define for me rule number 3. You're not going to see that in a quiz or in a test, but I will want you to know how to do this rule. So the integral of a constant multiple of a function. So that just means you have a constant being multiplied by whatever it is you're trying to find the antiderivative of. And so you are allowed to multiply the constant out in front. Okay, so that's my everyday explanation. Your constant can just move to the front. So if your constant's being multiplied by a function, just move it to the front and kind of move on from there. So let me show you what I mean by that. Let's look at an example or two. So if I tell you to find the antiderivative of 2x cubed dx, remember that just means, dx just means that I'm using the letter x. So when you go to take the antiderivative, the 2 is just going to pull over, and then you're still going to do the process that I've mentioned before. You are going to add 1 to the power. Okay, notice I'm leaving a space, and then you're going to multiply by 1 over that new power. Okay, and then don't always remember to put your plus c. So 2 times a 4th is just a half. So a half x to the 4th plus c would be your final answer for the integral of 2x cubed. Notice we could check it, right? Find the derivative of this, move the 4 to the front, and you're going to get 2x cubed. We're good to go, right? So especially at first, my strong suggestion is for you to check some of these. All right, let's look at the next rule, which is called the sum rule. Now, sum means addition, but just know this works for difference also. It works for subtraction. Addition and subtraction are kind of equal operations. This is going to look a little uglier than it actually is. Okay, I think you'll see when we look at these in practice, they're really not so bad. So all it says is that if you're taking the antiderivative of two functions being added to each other, okay, so like two separate functions being added or subtracted to each other, that it's the same as if you looked at them separately. Okay. Notice both of these had to end in dx, right? Because that's just notation. So in practice, all that means is that if you can split the functions up into separate pieces, then and then just do your power rule or whatever rule you need to do multiple times. Okay. So notice this is the antiderivative of x squared plus x cubed. So in my mind, I can just think of this as the antiderivative of x squared plus the antiderivative of x cubed. In other words, I can kind of think of them like separate entities. So remember your power rule for antiderivatives. You are going to bump the power up by 1, multiply by 1 over the new power. Okay, and the same thing for the second function. You're going to up the power by 1 and multiply by 1 over the new power. And then don't forget always to add your c. Okay, and again, we could check that really quickly, right? The derivative of this would be move the 3 to the front, x squared, right? Check. Okay, if you move this power to the front, you'll get x cubed, so we're good there too. Okay, so admittedly, it does take a little thought, right? Especially if you're so used to doing the power rule for derivatives, it takes a little extra thought to go backwards, okay, which is kind of what we're doing today. So, you know, whatever pacing you need to take this in order to get it correct, then do that. All right, so just like with derivatives, I really want things to look like exponents before I can begin to do antiderivatives. So notice, I had to repeat my integral symbol because I haven't done the bump the power up by 1 thing yet. Okay, all I really did is rewrite over x squared as x to the negative 2 power. So let's see if we can figure it out. First of all, any constant being multiplied by a function just comes down, right? Okay, and then let's talk about this, right? What's the understood power for x? It's 1, right? So if I increase the power by 1 and multiply by 1 over the new power, okay, I'll mess with that in a minute. The second part, I'm going to bring the constant down and I'm going to do the same thing. Just be a little careful with negative numbers, okay? If you add 1 to the power, you're not going to get 3, right? Or negative 3. If you add 1 to negative 2, you're actually going to get negative 1. And then multiply by 1 over the new power. As always, remember your plus c. So in the end, okay, 2 times a half goes to 1. So this is just x squared. 2 times negative 1 is just minus 2x to the negative 1 plus c, which could be simplified as x squared minus 2 over x plus c. Okay, so not trying to beat a dead horse, but again, take the derivative of x squared, you get 2x. Okay, if you take the derivative of this, you would move the power around to the front, you would get 2x to the negative 2, right, which is exactly what we changed that to, so we're good to go. So once you get the hang of this rule, even problems that seem to have really a lot of parts should be completely doable for you. Okay. So on a problem like this, the first thing is I would want everything possible to look like a power. So I'm going to continue my integral symbol. By the way, notice the integral symbol is large, right? It encompasses like all the pieces after it. So this is going to be plus x. So what does this change to? It's 1 over x to the third. So it's just going to be x to the negative 3. The square root, remember, those are just fractional powers. and then plus 4 dx. Okay, everything looks the same as far as notation goes because I haven't done anything yet. I haven't done the antiderivative yet. So let's go a piece at a time. Bring the 3 down, and then bump the power up by 1 and multiply by 1 over the new power. Okay, notice the order that I do that in I think is the best taught way. Okay, so I leave a little space for my fraction and I bump the power up by 1, and then whatever number's here I repeat here. Okay. What about on the next one? Notice the understood power there is 1, right? So if I bump the power up by 1 and multiply by 1 over the new power, I get that. Okay, now I'm on to this term. Okay, so add 1 to -3 and you get -2, right? So the new power is going to be -2, 1 over the new power. Okay, maybe just be a little careful with fractional powers, right? So if I add 1 to the power, I'm going to get 3/2. And then I'll have 1 over 3/2. Okay, notice there's always a matching here and here. The exponent and the denominator of your term is always the same. And then this is weird, but remember we're going backwards. So which type of function would give you an answer of 4 or a derivative of 4? It would be 4x. And then don't forget your plus c. So in the end, always clean up anything you can. So we get x cubed plus 1/2 x squared. Minus 1 over 2 x squared goes to the bottom since it's negative. Here, remember what I said, when you divide by a fraction, you just flip it. So that's going to be 2 over 3 x to the 3/2 plus 4x and plus c. Okay, so if you want to, maybe pause the video right now and check this. In other words, take the derivative of this long thing and see if you don't get back this original. Okay, and spoiler alert, you will. All right, so what about some of our special cases? So what about the indefinite integral of the exponential function? Remember, the exponential function is just e. Well, if you remember what the derivative of e is, it'll probably make this easier. But notice I'm doing antiderivative, right? So the antiderivative of e is just going to be itself, since the derivative of e is itself, okay? But then don't forget your plus c at the end. By the way, this is just for plain old e to the x. We'll have to deal with e to other more complicated powers later, okay? But for now, we're just going to deal with e to the x. All right, so I want to introduce to you the other special case. Remember, we learned these together, e and ln. So I think this one is maybe the more challenging of the two special cases. So the indefinite integral of the function f of x equals 1 over x, or x to the -1. Remember, those are equivalent. So the first thing to notice is go back to the power rule if you need to, but the power rule doesn't apply when the power is -1. If you go all the way back to it, it says it works for every single exponent except for when the exponent equals -1. Okay, so the exponent can be -2, it can be -3, it can be anything, but it can't be -1. And so here is the rule. If I want to do the antiderivative of 1 over x dx, so let's think back to derivatives. Which type of function gives you 1 over x as its derivative? Well, remember, that's the special case ln. So the natural log of the absolute value of x plus c is what you get here. So I'm going to kind of circle that in. This absolute value bar is only because you can't take the log of a negative number, or 0 for that matter. Okay, so just remember, this is your one rule breaker. Okay, we can't use it when the power of x is -1, so we have another rule for that. All right, so let's kind of mix in some of these new cases with some of the older things I know, or that we should know. All right, so remember, I want to find the antiderivative. So which function would give me 1 as its derivative? That would be 1x, right? Think about this also. I would bump the power of x up by 1. Notice I don't have a power of x, right? So if you bump it up by 1, you have x to the first. Okay, so that's another kind of weird way to think of it. What about here? If we bump the power up by 1, we'll get x squared times 1 over 2. The antiderivative of e is just itself, and then we'll add c to it. So that's it. Okay, and again, a really quick check. The derivative of x would be 1. We're good there. The derivative of this would be move the power to the front and you'd get x to the first. We're good there. The derivative of e is itself. We're good there. And the derivative of any constant's just 0. So I think we're good to go there. So be on the lookout for your special cases. All right, so what about this? Now notice, we're dividing, okay? And we don't have a rule for, we don't have a quotient rule for antiderivatives, if that makes you feel better. It's not that we don't know one now, like we never will have one, okay? So maybe that makes you feel better, maybe it doesn't. All right, so first let's see if we can rewrite this. Now when you have a single denominator, you're allowed to pull apart the pieces and put them each over the denominator. So in other words, this is really just asking me to find the antiderivative of 1 plus 1 over x dx. Okay, notice I'm still continuing the antiderivative symbol because I haven't done that process yet, right? All I've done is kind of algebraically change this. So what's the antiderivative of 1x, right? If I took the derivative of x, my derivative would be 1. This is my special case, right? So this would be plus the natural log of the absolute value of x, and then don't forget your plus c. Okay. Just kind of a quick check. Notice your rule for antiderivative is to bump the power up by 1. If you were thinking about this, if the power is -1 and you add 1 to the power, you would get x to the 0 power, right? So something happens with that rule and it just doesn't translate when x is -1, okay, or sorry, when the power is -1. So just kind of keep that in mind. To be honest, you're just going to need to be on the lookout for that special case, okay? But remember, it's only for 1 over x, not 1 over x squared, that's fine. 1 over x cubed is fine. It's only 1 over x that gives us this special case. So let's try one more, kind of like that, because I think that can be a little bit of a challenge. All right, so kind of like the last one, I don't really want to deal with this as a division, so I'm going to split it up and say x to the 5th over the denominator minus 2x over the denominator. And I'm careful to do my notation every time. So if I work this out, this is going to be the integral of x, right? X to the 5th. This would go away, right? Leaving 1 here. Here, this would cancel, leaving a 3, right? So how am I going to rewrite that? This would be minus 2x to the -3. All right, so now let's do antiderivative. Remember, we're bumping powers up by 1 if possible. Okay, so if we bump that power up by 1, we get x squared multiplied by 1 over 2. Notice this is not our special case. The power is -3. The only one that works with this special case back here is if the power is -1. So here we can just bump the power up by 1. So I'm going to move down the -2. If I add 1 to that, I'm going to get x to the -2 power, and then 1 over the new power. So the -2 comes from this constant, the 2 that I'm pointing at right here. This comes from us bumping the power up by 1. Okay. And then notice if you clean this up, by the way, these cancel each other out. So you end up just getting 1/2 x squared plus 1 over x squared. And then don't forget your plus c. Really, I should have had it here also. Okay, I rewrote this one as 1 over x squared because it's a negative exponent. Okay, So there's no more rules for today, but let's look at some example problems of what you might see in your homework and just maybe get our feet wet with this new thing called an antiderivative. So I want you to find the function f of x. If we don't know the original function, but we do know that the derivative of that function is 3x squared minus 4x plus 8. And we also know that when we plug in 1 to this mystery equation, we get 9 for an answer. So notice, we are not asked to find the derivative, we are given the derivative in this problem. Okay? We're asked to find the original function. So hopefully you understand notation-wise, but this is asking you to find the original f of x, and we're going to do that by finding the antiderivative of what we already know the derivative to be. Okay, and that'll land us back at the original function. All right, so let's do our process. So constants move over, and then we bump the power up by 1 and multiply by 1 over the new power for every part, right? So the 4 is going to pull over. I'm going to bump the power up by 1, multiply by 1 over the new power. And then the antiderivative of 8 is just going to be 8x. And then we're going to have plus c. Okay, we don't know what c is. So far we have most of it now, right? So if you work this out, okay, notice these are going to cancel, right? A third times 3 is just 1. So we're going to get x cubed minus 2x squared plus 8x plus c. But we're not done, right? So now we're going to find c. And notice we have something that we can use to be able to find c. We know that when we plug in 1 to this mystery equation, we're supposed to get 9. Okay, so let's see what happens. So if we plug in 1 as we have it now, we'll get 1 cubed minus 2 times 1 squared plus 8 times 1 plus that number c that we're not sure about. And we're supposed to get 9 for an answer. So use your calculator and figure all this out, or you could probably just do this one in your head, right? 1 minus 2 plus 8 is just going to be 7. So 7 plus c equals 9, right? So what must c have been? C must equal 2. Because 7 plus 2 equals 9. So in the end, we have a full function now. We know that it was x cubed minus 2x squared plus 8x plus some constant, and now we know that constant to be 2. Okay. By the way, notice we can check our work, right? Not only can we plug in 1 and make sure we get 9, but we can take the derivative of this guy and we'll get back this again. Okay. So you can really check a lot of these questions all around, and frankly, if you're a little shaky on derivatives, that might be a good idea because you'll learn the new process, antiderivatives, plus you'll be reviewing in your mind what derivatives were as well. So I'm going to be lazy. I'm going to say same instructions. So in other words, I'm going to give you the derivative, and I'm going to ask you to find me the original function. And I'm also going to give you a hint as to what c is by telling you that f of 1 is 10. All right, so if I want f of x, then I'm going to need to do the antiderivative of what I was given. And notice how I rewrote that. Okay, the only thing I rewrote was I rewrote the fraction as x to the negative 2. Okay, remember, always end your antiderivative stuff with dx, or if it's t in the problem, you say dt. All right, so let's find the antiderivative. The antiderivative of 1 is 1x. The antiderivative here, you just bump the power up by 1. Remember, the only time power rule doesn't work is if you have a negative 1 in your exponent. Okay, so if I bump the power up by 1, I'm going to get 1 over the new power will be negative 1. So notice always repeats here and here, always, always. And then plus c. So I have a start to what f of x is. I know that it's x minus 1 over x. But then I have plus c, and that's supposed to be 10. Okay, according to this statement right here. So now let's test it and see. So if I do f of 1, Then I'm going to get 1 minus 1 over 1 plus some number. I'm trying to figure out what that number is. Okay, equals 10. But notice these go away, right? So you're just left with c equals 10. So in the end, we get our final result for f of x is x minus 1 over x plus 10. Okay. Notice all I'm doing is rewriting this and sticking the c in that I found. Okay, so again, you can do two checks. You can make sure that you get 10 when you plug in 1, okay, and you can also take the derivative of this and verify that you get that back again. All right, let's do one more, and then we're going to look at maybe one application problem. So one more with the same instructions. So let's say that I tell you the derivative is 1 plus e to the x plus 1 over x. And I tell you that f of 1 is going to be 4 plus e. Okay, don't let that f of 1 number throw you off. E is just a number, right? So it's just 4 plus a decimal number that goes on forever. Okay, so let's just see if we can figure this out. So we want to get back to the original, and I'm going to do that by taking the antiderivative of what I have here. Now I'm going to leave this as 1 over x dx. Hopefully you recognize that as your special case. Okay, you can rewrite it as x to the negative 1 if you want, but we can't use power rule on this. Okay, this is our special case, and this is a special case too, actually. So the antiderivative of x is just 1x. The antiderivative of e is just itself. This is our special case, the antiderivative of 1 over x. So think to yourself, which function gives me 1 over x as its derivative? And the answer is ln. Remember, we have to do these absolute value bars to just verify that we don't get a negative number there or 0. And then we're going to say plus c. So here's my function, almost complete, right? X plus e to the x plus the natural log of x. But what I really need to know is what's that c going to be? Okay, so before I proceed, let's just make sure. What's the derivative of x? 1. We're good there, right? What's the derivative of e to the x? Itself. What's the derivative of the natural log of x? 1 over x. So I think we're good there. Now the question is, what is c, right? So notice, up here it says if we plug in 1, notice we're going to plug in 1 everywhere there's an x, then we're supposed to get 4 plus e. Okay, so maybe use your calculator, but the natural log of 1 is just 0. Okay, you can verify that if you want to, but the natural log of 1 is 0. So you're going to get 1 plus e plus c equals 4 plus e. So there's a couple of things you can do here. You can subtract 1 from both sides. You can even subtract e from both sides. And notice what's going to happen when I do that. They're going to go away here, right? That's going to go away. And I end up just getting c equals 3. Okay. Notice that's what I wanted, right? So in the end, my completed original function is x plus e to the x plus the natural log of absolute value of x, and then plus 3. Okay, it is important on MyMathLab that you put that absolute value of x. Okay, I think sometimes it'll go ahead and start you off with that, but you're definitely going to need to make sure that you put that in your answer. All right, so final question of this lecture. And then just know that we're going to stay on antiderivatives for a little while, okay? Maybe not quite as long as we did derivatives, but definitely expect this topic to stay around. All right, so let's look back at some of our topics from before. So let's say the marginal average cost in producing X number of sports watches is negative 1,000 over x squared. Okay, remember average cost looks like C bar, and then because it's marginal, remember the word marginal means derivative. Okay, and let's say that we know that regular old C bar of a 100, okay, so notice I didn't use the derivative notation there as 25, where C bar of X is the average cost in dollars. So I want you to find the average cost function, not the derivative of it, because I already know that. I want to go back to the original average cost function, and the total cost function. And let's see if we can figure out what the fixed costs are also. Remember, fixed costs are those costs that don't change, right? If I make one item, the fixed costs are set. If I make 1,000 items, the fixed costs are set. So part of this problem is realizing that marginal means derivative, right? So marginal average cost is exactly what they gave us. But what we want is we want regular old average cost. In other words, we just want C bar of X. So we know the rate of change, but we don't want the rate of change. We want what the pattern was originally. So to do that, I'm going to need to take the antiderivative of what I know the derivative to be. Okay, notice how I changed it, right? I didn't write negative 1,000 over X squared. I wrote it as a power. So don't let this throw you off because there happens to be bigger numbers. Pull the constant down and do your process, right? I add 1 to the power, I multiply by 1 over the new power. So 1 over negative 1, and then x to the negative 1.
Oh, I'm sorry.
So in the end, you'll get 1,000 over x plus a constant c. Okay, now it's a little weird, right, that we have a constant c and a cost c. So if you want to change that c to like a k or something, you can if that throws you off. But this is going to be our average cost function. But just like the problems before it, we don't want to leave this constant. So I'm going to even label this so that we don't get it confused. This is constant c, not cost c. So if we plug in 100 to this mystery equation, we're supposed to get an answer of 25. So let's see how we can make that happen. So we're plugging in 100. We're going to add some number, and we're supposed to get 25 for a response. But that works out to be 10. So 10 plus c equals 25. So the constant in this problem is just 15. All right, so now we have the average cost function. So the average cost is C bar of X, right? And here is the equation. We're going to repeat this, right? It's 1,000 over X plus what we just found the constant to be. Okay, so that's one thing I asked you to find. And so lastly, now we want to find the total cost function and the fixed costs. So it's been a little while, so let's review real quick. Remember that if I was trying to find the average cost function, that is, the formula for that is cost over X. So this is what I have. I know that this is I already know the answer to this, right? I already know that the equation is 1,000 over X plus 15. So we need this to look like this, and notice we have this plus 15 kind of hanging out there. So we're going to multiply, consider this to be over 1. We're going to multiply by x over x so that we can combine these together. Notice when I do that, I get 1,000 plus 15x over x. So now notice we have something that looks like c of x over x. So c of x is going to be 1,000 plus 15x. Okay, in other words, whatever you got on the top. Once you write it as c of x over x, it's just whatever the numerator was. And then which part of this represents the fixed cost that is unchanging? Notice the 15 cost will be multiplied by however many items you make, right? But the fixed cost, the amount that's just being added no matter what, is the $1,000, right? So the fixed cost in this case is $1,000. So the challenge in today's lesson is I'm asking you to go backwards through a process that maybe some of us still aren't comfortable going forwards through that process. So that's a little bit of a challenge, admittedly. Okay, so maybe before this lesson, if you were just completely lost in this lesson, you might want to go back and review derivatives a little bit and then maybe try to watch this again. Okay, but remember, antiderivatives, just like the name implies, is opposite, right? You're being given the answer as far as the derivative goes, and you're being asked to backtrack and figure out what the original must have been.